Good afternoon. Welcome to the CERIAS Security Seminar from Purdue University. Our speaker today is a PhD student here at Purdue, working for Professor Patrick Yoigster. His topic is Practical Confidentiality Preserving, Big Data Analysis, and Untrusted Clouds. Savas Savitas.
Thanks very much for the introduction. So today's talk is going to be about practical confidentiality preserving big data analysis in untrusted cloud infrastructures. So there's a few things we need to talk about. So we need to talk how we preserve confidentiality and how to do so in a practical way. So I will be presenting a few optimizations that achieve that. Our domain is big data analysis. So I'll talk about what tools we use to leverage parallelism to also deal with big data. And we are dealing with third-party cloud infrastructures, which means we need to find an elegant way to, even if we outsource our data, we'll have to keep them confidential. So this project is a joint work with another PhD student called Julian Stephen, Russell Sadel, and Professor Patrick Yoigster. Okay, so what's the problem we want to solve here? So I have a phrase here that I picked up from an article called RIP server, interestingly enough, last March, which says, today running your business on private servers is on the same level of odd behavior as carrying scuba tanks to provide a private air supply. And the article went on to talk about how the third-party cloud provided today, it has become very cost-effective, which it almost doesn't make sense for companies to have their own servers, spend the time and effort and money to create their own servers to support their services. So although this article didn't talk about confidentiality issues, so if you want to use such third-party clouds, you have to send your data to them. So can we really trust these infrastructures to hold their data, our data? And since security doesn't come for free, do we trust that they'll do everything they can to keep our data safe? Or can we trust the cloud providers themselves that they won't look into our data? Those are the issues that we're trying to eliminate. So for those who followed this seminar, we were lucky enough to have Larry Ponemon be here last semester to talk about how expensive or how costly are data breaches. And I have 3 points here that I took from a study that the Ponemon Institute did. The first point says that 36% of business critical applications are hosted in cloud. 30% of business information are stored in the cloud. And this study was done in last June, I believe, so these numbers might have gone up by now. But perhaps most importantly, the third point says that the more we use the cloud, the more likely it is for a data breach in such cloud to be very, very costly. So to reiterate the challenges we're trying to solve, we're trying to, what we want is use these cloud infrastructures more, but we also want to do that in a way that doesn't compromise confidentiality. So that's what the project tries to do. So how do we preserve confidentiality? So the technology we use is homomorphic encryption, which in general, homomorphic encryption allows you to encrypt your data. And even though your data is encrypted, you still are able to perform operations over them. So it comes in two flavors. The first one is fully homomorphic encryption, which allows you to encrypt your data and you can perform additions and multiplications on your encrypted data. And based on that, you can build circuits that can compute and can perform any type of computation. The downside of fully homomorphic encryption, though, is that it's not very practical. So it hasn't been around for too long. It's been around since 2009, I believe. And the schemes that support fully homomorphic encryption are so far not very practical, both in time, in size, overhead, but also in expressiveness, which means that there's a lot of effort required by the programmers to program these circuits that perform arbitrary operations. So I suppose the middle ground between fully homomorphic encryption and not using homomorphic encryption is partially homomorphic encryption. So partially homomorphic encryption allows you to encrypt your data and operate on your data, but only with respect to a certain operation. For instance, addition, multiplication, and so on and so forth. So an example here, the Palier crypto system allows you to encrypt data, and even though you have your data encrypted, you're still able to perform additions. The El-Gamal crypto system allows you to do multiplications. So to dig into that a little bit further, you have a value x1, which you encrypt. You have a value x2, which you also encrypt. And then you perform some operation on top of these two ciphertexts. And once you decrypt it, you get the result, which is supported by the specified homomorphic encryption scheme, be that an addition or a multiplication. And on top of that, there are schemes that are deterministic, which means that if you encrypt the same value twice, you get the exact same value, hence the name deterministic, which then allows you to do equality comparisons on ciphertexts. And also, there are schemes that support order preserving, which allows you, if you encrypt two values, the order of those values is preserved, and hence you can do inequality comparisons. So how do we use this technology to benefit the cloud? Well, if you want to do something like 2 plus 3, a very simple computation here, we encrypt 2, we encrypt 3, and send the encrypted versions of our data in the cloud. So our cloud only ever sees the encrypted versions. Then we apply some operation in these two encrypted versions, and we get the output. The output is also going to be encrypted. So the cloud never sees any plain text data. So once we're done with computing, we send the result of our computation back to the client side, which is the trusted side. We then decrypt, and then we get the results in its plain text form. Okay, Crypsis is the name of our system. So what's the Crypsis Intuition? Well, we try to avoid fully homomorphic encryption to avoid the overhead that comes with FHE. And we instead focus on using PHE, the partially homomorphic encryption. And the idea here is that you can find data flows within your scripts that you want to compute that only use set-and operation. So you identify those paths and those data paths, and you encrypt your data under that scheme that supports that operation. And on top of that, you can encrypt your data under multiple encryption schemes. So if you don't have conflicting operations, you can support multiple operations as long as the computation is separate. Although you do get times where partially homomorphic encryption is not enough. And what we do there, we still don't use FHE. We instead use re-encryption. And the idea of re-encryption is to have the data sent back to a trusted base. It could be the business or the client who initiated this computation. Have them decrypted, encrypt them under a different scheme that supports the operation you want to perform, and send the data back to the cloud, and then you can proceed with computation. And by doing that, we hope to perform better than fully homomorphic encryption. Okay, so some background. So we want to leverage the cloud infrastructure. So to do that, we use the MapReduce framework. More specifically, we use Hadoop, which is an open source implementation of this framework. But to avoid dealing with Hadoop directly, which for those who have played with it, code can get quite involved, we use Apache Pig. Apache Pig is a data flow language which ultimately transforms into MapReduce jobs. And it comes into parts. So you have the Apache engine, which does this transformation. And then you have the Pig Latin language, which expresses big data analysis jobs in a simpler manner. So this is an example of a Pig Latin script. First, in operation A, we load a file called infile, which has two columns, A0 and A1. Then we'll filter some information out. So we only keep information for which column A0 is greater than 10. Then we group according to the second column, A1. And then for each group, we sum all values of A0 before we store the results to a file called outfile. Okay, moving on. So this is an example that demonstrates the intuition of Crypsis, our system. So in this script, on the left-hand side, on the purple-ish color, we want to perform operations with respect to order-preserving encryption and additive homomorphic encryption. So what we do is, if you notice, we load a column named A, and we load it twice. We load its OP version and its AHE version, And that allows us to first do filtering based on a condition which uses greater than. So that uses the OP version of A. And then we perform an addition which uses AAG. Now on the right-hand side, in orange, reddish color, we load two different columns, B and C. And these columns are both loaded in MHE. And they're loaded in MHE exactly because we want to perform multiplication, which is what we do in B1 here. And we can choose to store the result. It might be interesting on its own accord. But what we want to do next in operation D is add the result of the left branch with the right branch. So the result of A in A2 is, since it is the result of an addition, that's encrypted in an AAG scheme, which supports addition. But B1, it's encrypted under MAG, since it's the result of a multiplication, which means when you want to perform this addition here, you cannot proceed unless you first re-encrypt, which is what we do here. We have a step to re-encrypt our data, B1 specifically, from an MAG scheme to an AHE. And once we do that, we're able to proceed with performing the addition and then storing our result. Okay, moving on. So this is the high-level idea of our architecture. So we have, in the blue box, our trusted tier. This is held within our business, or this is the client who initiates the computation. And on the right-hand side, in the red box, we have the cloud infrastructure, which we cannot trust. So how does the computation happen? Well, the user submits a source script. This is a script that operates on plain text data. And the first thing we need to do is transform this script so that it operates on encrypted data. So this script is submitted in our script transformation module, and it communicates with our encryption scheme module so that it performs the necessary transformations. So there's two things that need to happen here. First, the script needs to be encrypted, and two, after we analyze the script, the encryption module needs to take over to figure out what kind of data is used in this specific script, then take the plain text data from the unencrypted database, which is held in a secure base, encrypt the data, and send the encrypted data to the untrusted database. So once these two things happen, we're able to proceed with executing the script. So the execution handler sends the target script. We call target script the script that operates on encrypted data. So it sends that to the peak service that runs on the cloud, and the script is performed. So another key point here is that we use an unmodified peak service, which means we never changed anything in the peak, Apache peak code. And we managed to do that by introducing a set of Crypsis UDFs. These are user-defined functions. And what are these used for is to replace the operations such as addition, subtraction, multiplication, and aggregation functions too, with the versions that perform the exact same operation but on encrypted data. So a lot more information about that can be found in our paper, which appeared in Cloud 2014. I suppose another thing to note here is that the untrusted tier, so the cloud, only ever sees the public keys. That's what PK stands for. And the secret keys are only held in the trusted tier. Okay. Now, how do we perform our transformation? So the transformation of scripts happen in 3 steps. On the first step, we analyze the script to identify the data flow paths. And after the step, we generate a data structure, which is a directed acyclic graph, with the nodes being the operations, such as load for each, or store, etc. And the edges connecting these nodes denote how these operations, how the data flow from one operation to another. So once we do that, we generate a map of expression trees. So each of these operations might contain expressions, and we parse all these expressions, and we generate a map containing all these expressions, and we keep track which tree belongs to which operation. And finally, we generate a data structure called a set of annotated fields. And what this data structure basically holds is for each field, So you can think of field as the columns of data or the columns created throughout the computation. So for each field, we keep track of what kind of or properties, are homomorphic properties, each field is required to be under, and what homomorphic properties it is available under. So once we have these data structures, we're able to transform our script. And well, an interesting case is how do we identify when re-encryption is required? So I have two different expressions here. The first one doesn't need re-encryption. The first one is a greater than 10. And if you notice here, the leaf nodes show that a column A, and the literal 10 are available under an OP scheme. And then the greater than operation requires an OP, which means you don't need re-encryptions here. The required schemes are available. The second one, which is A plus 5 times B, you start, well, starting from bottoms up, you have the leaves, which are available in an AAG, that's A and 5 are under an AAG scheme, and that allows us to do the addition. But now you want to do a multiplication, which requires MAG encrypted data. You have that for column B, but you don't have that for the results generated for after the addition, which means you cannot proceed unless you perform a re-encryption, which is what we do here. We insert a node denoting that we need to re-encrypt our data, and that creates an expression tree that can be computed. So as you can imagine, I suppose re-encryption is a very expensive operation. You have to send your data back to the cloud, back to the client, decrypt them, encrypt them again, and send them back to the cloud. So we first tried to see how much this re-encryption is used. So we analyzed the PIC mix benchmark. This is a benchmark used to evaluate the PIC engine itself as they updated it, which has 17 scripts in total. And we found out that only in one of those scripts requires re-encryption. So that was very encouraging. And another one required the same data encrypted under more than one encryption schemes. So this is an example of a source script and a target script. So that's a source script that operates on plain text data and a script that operates on encrypted data. So we start by loading, let's see the source script first. We start by loading a file called employees, which holds two columns of data, the salary and the department of each employee. And we save that in an alias called emp. We then filter based on salary. So we keep only the high paid employees that have salary over 80,000. Then we group the remaining employees based on department. And then for each of these groups, we create, we save the group, which is the department, and we sum all the salaries together. And then we store the results. So let's see how we transform this script. We first load a file, which is not the same. We load the employees enc, which is the encrypted version of the same file. Note that what used to be salary is now salary encrypted under OP and AAG, and that's because our script identified that salary is involved in both inequality operations and in addition. And then the department is involved in deterministic, so equality comparison, so we load the deterministic version of department. So in the filter operation, we then replace the greater than symbol with an encgt, encrypted greater than, and this is a UDF, a Crypsis UDF, which replaces the greater than operation with the same operation but performed on encrypted data. So that of course uses the OP version of salary. And we also encrypt literals, right? We don't want to leak this information. So we encrypt the 80,000 here to a number which, so here the ellipsis shows that the number is quite large. So we don't have the whole thing showed here. We then do the group using department deterministic version. And then we generate the group and also the sum of all salaries. So here's when salary AAG comes to play. And again, we replace not only operations, but also the aggregation functions with our own functions. Okay. So a lot of information about these transformations appears in our paper in AAC 2014. So anyone who wants to read more about that can refer to that. So I copied the target script here. This is not exactly the final version that is sent to the cloud, because we might have our data encrypted, but even so, the script itself might leak some information. So before we send the target script to the cloud, we first perform one more step, which is to obfuscate the names. So what can we learn from the target script? So the data is encrypted, but we cannot read the data, but we know that the data is about employees. That's already an important information that shouldn't leak out. We know that first and second column of the data of the file refers to the salary of the employee, and same for the third column refers to the department. What else do we know? Well, we learned that we filter out some salaries, and from EncGT we learned that we only focus on the probably high-paid employees, as the name indicates here, high-paid. Then we group by the department, and then we sum over the salaries. So we learned a lot by just looking at that script. So we replace this script by the obfuscated target script. So we replace all the alias names with A, B, C, etc. We replace the file name with a name that doesn't infer information. Same for the columns, and same for the function names. Okay. Okay, so about our implementation now. So I mentioned how we first transform our scripts, and we do that by using a compiler. So this compiler's job is to figure out how and transform a script, and then do the transformation to generate the script, the target script, and also obfuscate the names. But also it's responsible to identify possible optimizations and make the appropriate changes to the script so that these optimizations will apply. Then I mentioned the Crypsis UDFs, which are the functions that replace operations with same operations on encrypted data, which of course allows us to use an unmodified peak service. And I suppose this allows, well, compared to other services, similar projects rather, our expressiveness is quite wide, because we can do additions, subtractions. The squiggly line here stands for negations, multiplications, exponentiations, equality comparisons, inequality comparisons, and a bunch of aggregation queries, functions, just like, for example, sum, max, etc. We also support negative numbers and floating point numbers to a certain extent. Okay, so I did say this is a practical confidentiality preserving project. So here we introduce a set of optimizations that allow these jobs to be executed in an optimized way. And we group our optimizations in 3 categories. So the first one tries to minimize the number of re-encryptions that need to be performed. Since this is a very costly operation, minimizing the number of re-encryptions gives us a lot of benefit. And I'll talk about 3 different such optimizations. The second group, well, it's just a single optimization, tries to eliminate the redundant computations. So we don't want to perform operations twice. Okay? And finally, the third group focuses on reducing the amount of data we perform computations over. So starting with the first 2 optimizations, the expression rewriting. So I have an example script here. So these scripts are the source scripts. I show the version that works on plain text data just because it's simpler to convey the idea. But you can think of these optimizations applying on the target scripts. Okay. So we start by loading, so let's focus on the first script. We start by loading a file with a single column called col, and we perform column times 2 and column times 3 to get x and y. So this means x and y are encrypted in an MHE scheme. And then what we want to do is x plus y times 2. So in order for us to do that, we need to re-encrypt x to an AHE scheme. So that's one re-encryption. Then we need to do the same for y, so that's 2 re-encryptions. Then we can perform the addition. And once we do that, we can do another re-encryption to re-encrypt the result into a multiplicative homomorphic encryption scheme, then do ×2, and then store the output. So we can do a bit better. So we have 3 re-encryptions here. If you see the optimized script, the first part is the same. So you do x and y, which are both in an MAG scheme at the end. And then instead of doing the addition first, you transform or you rewrite the expression to be x times 2. And since x is already under an MAG scheme, you can perform that. And similarly for y, without no re-encryptions. Then you need to re-encrypt the result of these x times 2 and y times 2 before you can add the two together. So that gives us 2 re-encryptions. So we reduce the number of re-encryptions from 3 to 2. That's a huge benefit. Okay, so operation reordering. So in this script here, we once again load the file with a single column. And what we do here is we perform an addition. We do column plus 10 to get x. And then we want to order based on x. So to perform an order by operation, we need the data to be encrypted under a scheme that supports order preserving. So before we can do that, we need to re-encrypt our data and then order them. So that's 1 re-encryption required. How can we do better? Well, if you notice, first of all, the addition we perform is with a constant, which means either before or after we do the addition, the order of the data doesn't change, right? Because we just add a constant. So we can leverage that, and instead of performing the order by operation after we add, we can do it before. So we reorder the operations here, and then once we do that, we're able to use the OPE version of the column to perform the ordering, and then use the AAG version of column to do the addition, which means we don't have to use re-encryptions at all. Okay, so this is the third optimization that tries to reduce the number of re-encryptions. This is probably more interesting and a bit more involved. And it leverages the fact that oftentimes we have files that hold many columns, and not all of those columns hold sensitive information. So how do we leverage that? We only encrypt the columns that hold sensitive information. So we benefit in 2 ways if we do that. First of all, by not encrypting our data, it means our data size doesn't expand. So overall, the size of our data is smaller. And secondly, we can use a secondary homomorphic property, which I'll explain in a minute, to avoid using re-encryptions. So before, if we wanted to do a computation of like a plus b times c, we need a re-encryption to re-encrypt the result of a plus b to an MAG before we can do the multiplication. Now, so far we talked about homomorphic encryption schemes that involve having 2 encrypted values and then combine them in some way, and then when you decrypt them, you get the result you want. Now, there's a secondary homomorphic property which involves you encrypting one of the 2 values, but having the second value in plain text. So you have x1 encrypted, but x2 is unencrypted, and then you can combine these 2 in some way, and when you decrypt the result, what you get, if this scheme is an additive homomorphic encryption scheme, what you get is the multiplication of the 2. So what have we achieved here is to perform a multiplication using an AAG scheme. So that's very important. And we can do the same for using an MAG scheme to get an exponentiation operation. So how do we use that? Well, let's first see how we would perform this computation here, a plus b times c, without this optimization. So we load a and b in an AAG scheme, and we perform the addition. And then before we do the multiplication, we need to re-encrypt our data from an AAG scheme to an MAG scheme. So we have 1 re-encryption, and then we perform the multiplication. So with this optimization, we once again perform the addition here, a encrypted add with B. But now, instead of re-encrypting, if we assume that column C doesn't hold sensitive information and we can afford to have it in its plain text form, then we can use the encrypted pmult, that stands for Pallier multiplication. Pallier, it's an additive homomorphic encryption scheme. And using this property here, we perform multiplication, even though the result of A plus B is in an additive homomorphic encryption scheme. So we avoid using re-encryption. Okay, so now we'll move to the second group of optimizations. This one's the repeated sub-expressions. Again, another example here. In this example, we first load a file with 3 columns: price of a product, discount, and tax. And we want to figure out what's the discount price. So we multiply price with 1 minus discount to find the discounted price. And then we want to see how much we need to charge for this product. So we again do price times 1 minus discount times 1 plus tax to get the discount price plus the tax. So if you notice here, we have a sub-expression which repeats in both these computations. We have price times 1 minus discount, which we perform twice, right? And we can avoid that to make things move a bit faster. So what kind of transformation do we do here? Well, we introduce an intermediate operation. We call discount here just for demonstration, which performs this sub-expression which appears in both computations. And we call that a disc price. We also include tax here just because it is involved in the next operation. So once we do that, we're able to just reference the discount price twice instead of computing the same sub-expression. Okay. So next optimization. This is very similar to the operation reordering, which I mentioned already, but it doesn't try to reduce the number of re-encryptions, but rather it tries to reduce the volume of your data you perform operations over. So what do we have here? We have a file that contains a salary and a rating of an employee, perhaps. And what we want to do here is give bonus to these employees, but not all of the employees, but rather those employees that are over 8. So that's exactly what we're doing. We first add 100 to all of the salaries, but then we filter out all those employees that do not have a good score, a good rating. So how can we improve the performance of this script? Well, what we do here is we perform computation over a set of data, but then we filter out some of that data. So what we can do instead is first filter out our data, so the volume of our data is reduced, and then perform the addition, which means you have less data to perform addition over. Okay, I think that's all there is to say about this. Well, and that can be, I suppose, generalized in the sense that whenever you have a filter whose order doesn't matter, you always want to perform filter first so that you reduce your data size. Packing. So this is the last optimization, and which again targets to reduce the volume of your data. So usually when we want to perform operations, we use numbers of 32-bit long or 64-bit long numbers. And when you encrypt those numbers, well, according to what key size you use, the size increases a lot. So usually nowadays we use a key size of about 1024 bits, or even that is not very secure nowadays, so we use 2048 bits long keys. So that means if you want to encrypt a 64-bit number, you'll get a number which is 2048 bits long. So that's a huge expansion in the data size. So what can we do about that? Well, so far we encrypted one value into one ciphertext. What we can do instead is pack a lot of numbers into a single plain text and then encrypt them into a single ciphertext. And we can do that for and additive homomorphic encryption schemes, but also for MAG, so multiplicative homomorphic encryption schemes. And how does this work? Well, if you think this box as being a single ciphertext, what you want to do is have x1 and x2n up to xn. You can get to choose how many numbers you'll pack within a single ciphertext. And then let's just overlook padding for now. And then when you add these two ciphertexts, what you manage to do is perform multiple additions of multiple values at the same time. A problem is whenever you do an addition or a multiplication, you might have overflows, which means unless you use padding, the overflow will leak into the number that comes next, and that will corrupt your data, which is why we introduce this padding here, which is a string of just zeros. So if you perform a bunch of additions here, and then you have overflow, the overflow will be caught in the padding, and then your data will not be corrupted. Okay, so I suppose we have time to talk a little bit more about packing and why the MAG version is a bit more limited. So I'm going to use the writing pad here. So how does packing work? So if you want to perform something like 1, you have to these 3 numbers, and you want to add these 3 numbers to 3, 4. How do we do this addition? How did we learn to do addition in elementary school, I suppose? Well, we consider each column separately. So we do 3 plus 4, we get 7 here, 2 plus 3, which is 5 here, 1 plus 2, which is 3. And we get the result. So the idea of packing acts the same. So usually this is a single number here, but the way we use packing, each of these numbers, it's separate. And then once we want to get the final results, we perform unpacking, so we get 3, 5, and 7, the numbers we require. So that's all well for addition. Now, for multiplication, things work a bit different in a sense that if we want to perform multiplication, let's just do something simple. There isn't a one-to-one correspondence. Instead, we need to multiply 2 with all 3 numbers, right? So we get 2, 4, and 6 at the end. So that's why things get a bit complicated. Here it's fine because when we unpack, we still get 2, 4, 6, which is what we wanted. But what if you want to have more numbers here? What if your calculation was 1, 2, 3 times, let's say, 2 and 2? What do we get here? Well, we first use the first number to get 2, 4, 6. Then we shift and do the same thing, 2, 4, 6. And then we add, so we get 6, we get 10, so that's 0 there. 4 plus 2 is 8, we get 9 here and 2. So what are these numbers? If we unpack, the results are not what we expected, right? Maybe what we expected here, if we were doing it column-wise, it would be 6, 4, and 1. So we get 1 and 6, the very first and the very last numbers, but in the middle, that's probably the number that we wanted. But it gets mixed with other values, which is why we cannot extract 4 from here. So MAG is limited when it comes to packing, in the sense that we can do packing times a constant, or if we have a calculation of this kind where you have 2 by 2 numbers, you can do that. But anything more than that, it gets more complicated. I think there was a question, or?
Yeah, 2 plus 4.
Did I make up?
Yeah, I think it's 7.
Okay, sorry about that. Yeah. Any other questions about packing here, or anything else? Okay. All right. So moving on, how did we evaluate our system? Well, the first evaluation we did was to see how much overhead does Crypsis give compared to the unencrypted version. So we took PicMix, which is the benchmark I mentioned before, and we execute all scripts in plain text, so without Crypsis, and then we do the same with Crypsis, so the encrypted version of the data. So the x-axis here lists all the scripts from 1 to 17. There's a total of 17 scripts. The red bars show these scripts, the runtime of the scripts in plain text data, so without our system. And the blue bar shows the same execution with Crypsis. So to perform this computation, we used 11 EC2 large instances with 2 virtual CPUs and 3.75 RAM each. Our data size was 5 gigabytes, which was over 3 million rows. And what we saw here is that the overhead was about 3 times, on average, was about 3 times compared to the time taken for the plain text data to be executed, which we think is a fair trade-off, since what we do happens entirely in ciphertexts, so it doesn't leak information. Anyone who compromises the cloud cannot see the data, the input data, nor the output data. And if we were to do that in fully homomorphic encryption, the overhead would have been much, much larger. So the second evaluation we do is to compare our system with another system that uses homomorphic encryption to preserve confidentiality. That system is called CryptDB. And the drawback of CryptDB, I suppose, is that it is implemented on top of MySQL, which gives it a centralized design, as opposed to our design, which is built on top of Pig Latin and hence Hadoop, which can be parallelized. So to see how much our system scales, we increase our data size here in terms of records, and we compare the runtimes between our system, which is the red point here, and CryptDB, which is the blue point here. So in the setting we use 3 machines for our system, since we can use parallelism, and 1 machine of the same type for CryptDB. And we see that as our data increases, we get up to 3 times faster execution times. And then the data we used, well, the largest data set we used was 7 gigabytes. So the comparison would have been a bit unfair because we use more resources, of course. So we also wanted to test how that compares in terms of cost. So this second plot shows the cost of each of these 2 versions, the CryptDB and Crypsis, our system, based on time taken for the scripts to execute, but also what kind of resources we use. And as shown in this plot, it seems that the cost in both cases is very, it's comparable. Okay, so some related work. I've already mentioned CryptDB, which is the comparison we made with Crypsis, which is, as I mentioned, implemented on MySQL, which has a centralized design and hence, when it comes to big data, we can scale better. CryptDB also doesn't support the notion of re-encryptions, even though it does support some computation on the client side. But if there's need to re-encrypt your data and proceed with computing on the cloud side, that's not supported by CryptDB. The second system here, so Monomi, is in many ways an extension of CryptDB in that it introduces optimizations to improve the performance of complex queries. But it's also implemented on Postgres, which also gives it a centralized design. And lastly, MrCrypt is another system that uses homomorphic encryption, and it applies transformation directly on MapReduce jobs. The limitations of MrCrypt or MrCrypt is that it doesn't support re-encryption at all. So if it finds situations where operations are not supported by the partially homomorphic encryption schemes, then it cannot proceed. Okay. So to summarize, so I started this talk mentioning how important the cloud computing is and how it's cost-effective design and it's pay-as-you-go, or the infrastructure on demand design, it's a much better solution compared to having our own servers. But that inherently have some confidentiality concerns in the sense that we cannot trust the cloud providers with keeping our data safe. And then I introduced Crypsis, which tries to give solutions to these issues by using homomorphic encryption, hence keeping our data encrypted. And also I introduced several optimizations that allows us to do computations on an efficient way. So for future work on this project, we're trying to come up with more fine-grained encryption systems. And what we mean by that is we can allow the user to not only give us scripts, but also gives us some metadata to tell us which columns are allowed to be encrypted and which are allowed to be in plain text. And that's where the selective encryption comes to play to gain more efficiency. And finally, since, like I mentioned, re-encryptions are very expensive operations, we are always looking for more optimizations to reduce the number of re-encryptions. So thank you for your attention, and I can take any questions or comments.
Questions?
Yep.
So you had mentioned that you had limited support for floating. Oh, sorry. You'd mentioned that you had limited support for floating point operations. I wondered if you could expand on the limitations there.
So when you encrypt a value, that usually only applies to integer or integral values. So when you have a floating point number, say 1, 2.3, 4, 5, 6, you cannot easily encrypt that and still be able to perform additions or other operations. So the way we support partially these floating point operations is by, given a floating point operation, we'll multiply that by a value that we set, say 100, which will give us 2, 3, 4 point floating point numbers. And then we truncate that to just the integral numbers. And then we perform operations as if this was an integer value. And at the end, we divide our results to go back to floating point numbers. And that's what we mean it's a limited support. Other questions?